for the kind invitation from the SEMNI community. Thank you also to all the people attending this seminar. And of course, a big thank you to Elias, Irene, and the rest of the SEMNI community for organizing this and also for awarding me the SIMO Prize. I am very pleased and humbled given the strength of the Spanish computational mechanics community. I joined SEMNI in 2012 when I was still a master's student. At that time, I was spending quite a lot of time with Oñate's finite element book, so I decided to look up in the internet what this Oñate man was doing. And I discovered not only that Oñate was an outstanding scientist, but there was also a very strong community of Spanish scientists leading computational mechanics discoveries at an international level. I was very impressed, and I felt that I had to be part of that, that I had to support those endeavors. So I paid a small fee that was in place for students at that time, and of course I never stopped being a member. Although my academic career has taken me away from Spain, which means that in addition to being a SEMNI member, I've also been involved with the Nordic Association for Computational Mechanics, and now with the UK Association for Computational Mechanics, two other organizations that also have a strong reputation and history. So today I'm going to talk about how the so-called phase field paradigm can open new horizons in the modeling of fracture, fatigue, and environmentally assisted damage. But before I start, let me emphasize that there are a lot of people that have contributed significantly to what I'm about to show. Not only the PhD students from my group at Imperial College London, the Mechanics of Infrastructure Materials Lab, but many other collaborators around the world. I have listed in the slide those that have been particularly related to the results that I'm about to show. So moving on, I will divide my talk into two parts, essentially. First, I will describe the phase field concept and its application to fracture, discussing at a high level the underlying equations and the implementation details, and showcasing some of the pioneering applications and developments that we've been involved in. In the second part, I will introduce this exciting scientific and technological challenge that is hydrogen embrittlement, and I will discuss how we have developed a mechanistic computational framework that can predict hydrogen-assisted cracking in both laboratory experiments and practical applications. And finally, I will discuss briefly a recent paper of us that shows how the phase field paradigm can be used to enable modeling another important challenge, the corrosion of metals. So let's start with the phase field paradigm that is becoming very popular in many areas. We all know that from a computational or mathematical perspective, tracking the evolution of interface boundaries is challenging. The idea behind phase field methods is to use an auxiliary field to follow interfaces implicitly, so to say, in the sense that we no longer have a sharp interface, but the auxiliary variable, so-called phase field, is telling us where the interface lies. So for example, in the case of fracture applications, the phase field can take the value of 1 in the crack phase and of 0 in the undamaged material points, varying smoothly in between. The temporal evolution of the phase field variable is then described by a differential equation that can be easily solved using standard numerical methods, making the tracking of evolving interfaces computationally tractable. The method was first developed in the microstructural evolution community, where the change in shape and size of microstructural features, such as grains, can be predicted by defining the evolution of the phase field in terms of other fields, such as temperature, through a thermodynamic free energy. While in fracture mechanics, the application that I will be mainly discussing, the phase field tracks the crack-solid interface, enabling capturing complex morphologies. You can see in the figure crack merging, nucleation from arbitrary sites, branching. So it's a very powerful tool from a computational perspective. I have worked with other computational fracture mechanics methods in the past, such as XFERM or Quasi-Newton models, and there's no comparison in my experience. And at this point, you may say, okay, all good on the computational side, no issues in dealing with evolving interfaces, such as cracks. But when do those cracks propagate? Or in other words, what differential equation do you use to evolve the phase field? Well, one of the nice things about phase field models is that they provide a computational framework for Griffith's energy balance. Those of you familiar with fracture mechanics will remember that Griffith, one of the fathers of the field, postulated that a crack will grow if the energy released by the solid reached a critical value, the so-called critical energy release rate, or material toughness, GC. This energy balance is the result of considering, in a thermodynamics context, the work required to create two new surfaces. And one can formulate Griffith's energy balance in a variational form, with a term accounting for the stored elastic energy in the solid, as given by the strain state, and for a second term characterizing the fracture energy, so the energy dissipated by the formation of a crack. Therefore, crack nucleation and growth can be predicted naturally without ad hoc criteria, as dictated by the minimization of this energy conservation statement. However, minimization of this Griffith energy functional is hindered by the fact that the crack surface gamma is unknown. And here is where the phase field paradigm comes to our rescue, because one can use the phase field as a marker, transforming the surface integral into a volume integral and enabling us to use this to solve this global minimality problem. Two things that I want to emphasize here. First, following standard continuum damage mechanics arguments, the phase field can be thought of as a damage variable that goes from 0 in intact materials to 1 in fully cracked materials. And as a consequence, by increasing its value, it will degrade the stiffness of the solid. You can see that in the first integral here. Secondly, there's a gradient term, and consequently, a length scale. There's a phase field length scale. So the model is non-local, which ensures mesh objectivity. Results are mesh independent as long as this length scale is resolved. So at the end of the day, we have a model that is physically sound based on Griffith and the thermodynamics of fracture, and at the same time computationally very compelling. You can get a good overview by looking at the balance equations. The first equation is the solution to the deformation problem, the standard balance of linear momentum with the phase field degrading the stiffness of the solid. And the second equation is the phase field evolution, sort of a competition between the strain energy density of the solid that increases with mechanical straining and the toughness, a material property. You can see it here. So just by solving this simple system, we can predict in both 2D and 3D very complex cracking patterns such as branching, merging, initiation from arbitrary sites, complex trajectories, and without convergence issues or the need for remeshing. For example, in the slide, you can see crack branching due to the application of a dynamic load. Red color contours denote the areas where the phase field equals 1, so the cracks, basically. But before I say a few things about how to solve that system, let me say something about the phase field length scale. This is a question that I get pretty often. From a numerical perspective, having a length scale is very convenient because it regularizes the problem. But this, of course, comes at the cost of adding one additional parameter. And people wonder about the physical meaning of this parameter. Having two approaches to this. Initially, the length scale was considered to be only a regularizing parameter, and it has been demonstrated using gamma convergence that the regularized functional converges to the Griffith functional as the length scale goes towards 0. Another approach is to consider the length scale to be a fixed material property, and if you solve analytically the homogeneous 1D problem or run a uniaxial one-element calculation, what you get is what you see in the slide. So a stress-strain relationship that resembles the traction separation laws of cohesive elements, and where the critical value of the stress, the material strength, is governed by the magnitude of this length scale. And you can clearly see the connection with the first approach. If the length scale approaches 0, then the strength becomes infinite, as predicted by Inglis and linear elastic fracture mechanics. But of course, in reality, materials do have a finite strength, and thus considering a finite value of the length scale is suitable. In fact, phase field models can naturally capture the transition from fracture-driven failure to strength-driven failure, thanks to the role played by this length scale. Those of you familiar with fracture mechanics will recall the concept of a transition flow size. If a crack is larger than the transition flow size, then one uses fracture mechanics, otherwise failure is driven by the mechanical strength. This is a concept that is very widely used in standards and design. And this is naturally captured in phase field fracture, as you can see in the slide. So the summary is that for short cracks, or in the absence of cracks, the length scale matters as it controls the magnitude of the strength. And for your results to be mesh insensitive, you need, of course, to make sure that your mesh is sufficiently fine to resolve this length scale. A rule of thumb is to make sure that your characteristic element length is 5 times smaller than the length scale. Well, for large cracks, crack initiation will be toughness driven. You can see in the picture of the right that cracking starts whenever the critical energy release rate is attained, independently of the value of the length scale. But you can also see that if you have an elastic plastic material, so if you have an arc curve, then the crack growth resistance behavior is going to be influenced by the magnitude of this length scale. Let me take you back to the system of equations. Remember that in addition to solving an equation for the displacement field, we have an equation for the phase field, implying that the phase field is an additional nodal degree of freedom. And remember also that these equations are coupled, so the phase field reduces the stiffness, and the displacement solution will change the strain energy density. So there are two obvious options to solve this system. One is what we call monolithic schemes, where we solve the displacement subsystem and the phase field subsystem simultaneously. This is ideal and in principle efficient, as the system is unconditionally stable. However, the total potential energy functional is non-convex with respect to the displacement and phase field solutions, and this causes convergence problems as the Jacobian matrix in Newton's method becomes indefinite. Another approach is to use a staggered solution scheme by which both systems of equations are solved sequentially. First, we get a solution for the displacement problem, and then with the resulting strain energy density, we compute a solution for the phase field. This is very robust, but the solution can be sensitive to the time increment use. However, there's a third option that combines the best of both approaches. If Quasi-Newton solution algorithms are used, such as the BFGS one, then a monolithic approach can be used without convergence problems. This has been demonstrated by Wu and co-workers for the phase field cohesive submodel, and by us for the conventional phase field formulation. Quasi-Newton methods are very robust when dealing with non-convex minimization problems. But let me briefly give you a taste for the robustness and efficiency of Quasi-Newton solution schemes. What you see in the slide is a square plate with a crack subjected to uniaxial tension. The solid is elastic and fracture occurs in an unstable fashion, so the crack propagates instantaneously across the entire width of the plate. You can see here the resulting force versus displacement curve in red. You can see that there's a sudden dramatic drop of the load carrying capacity as a result of the unstable crack growth event. And superimposed, you can see the load steps taken and the number of iterations per each load step. I want to emphasize two things. First, you can see that the method is very robust. Calculations run in a couple of minutes, and the entire fracture process can be captured up to complete rupture of the sample with only 30 load steps. However, you can also notice that the critical load step requires more than 200 iterations to converge. This is a characteristic of phase field fracture simulations. The scheme is very robust and convergence is always achieved, no matter how nasty the problem is, but critical time increments might require hundreds of iterations. And you can see here the comparison with a single pass stagger scheme. You can see on the left that for staggered schemes, the force versus displacement result is sensitive to the number of increments, as in explicit or Fore-Euler types of analysis. And you can see on the right that achieving the correct solution with a staggered scheme requires a number of iterations that is 2 orders of magnitude larger than with the Quasi-Newton solution schemes that we are proposing, which are very efficient. And I will finalize this part by just saying that Quasi-Newton solution schemes can be of great importance for the emerging area of phase field fatigue, because one can also extend the phase field fracture to model fatigue by incorporating into the equation the fatigue degradation function that evolves with the number of cycles. And the key thing here is that the staggered approach deviates from the real solution within each cycle, accumulating error and leading to inaccurate predictions. You can see in the slide a plot of crack extension versus number of cycles, and you can see that many hundreds of iterations of increments per cycle are needed to reproduce the accurate result with staggered schemes, which is captured, the accurate result is captured by our monolithic Quasi-Newton approach with only 4 increments per cycle. So it's a massive difference there. And yeah, I mean, I have had a lot of fun since I became aware of the phase field fracture method in 2017. So I will finish this first part of the talk by showcasing some pioneering formulations that we have developed to contribute to the success of phase field fracture. And I should emphasize at this stage that many other people have used this methodology to gain new insight into a wide number of problems, also within the SEMNI community, as is the case, for example, of Irene Arias and Pepe Reynosa. So the first application that I will talk about is shape memory alloys. We recently developed the first phase field formulation for shape memory alloys, phase field fracture formulation. These materials undergo phase transformation from austenite to martensite upon the application of a mechanical load, a change in temperature, or both. And as a consequence, they exhibit a nonlinear response with very large strains, up to 10%, that are reversible as the material can recover its original shape by unloading or through a change in temperature. And of course, both mechanical and fracture properties change with this phase transformation. From a fracture mechanics perspective, what is most interesting is that the high stresses that are present at the crack tip will trigger a stress-induced phase transformation. And as a consequence, there will be a small region at the crack tip or near the crack tip where the material is in its martensitic phase. You can see that in the slide for a calculation of a stationary crack, so no phase field. On the right, you can see the contours of the martensitic volume fraction. And on the left, you can see the stress distribution ahead of the crack tip in a log-log plot. So far away from the crack tip, the stresses are governed by the austenitic material properties. Then there's a transformation zone, and then close to the crack tip, when the material is fully martensitic. And the key thing here is that this stress-induced transformation brings some toughening of the material. And this toughening effect is captured nicely by phase field. I am not going to go into the details of the formulation. I will just show a couple of representative results. But here you can see the paradigmatic benchmark of the cracked square plate that I showed you before. However, in this case, you don't see a sudden drop in the force displacement response, and failure is much more stable. This is because of this toughening effect that is triggered by the phase transformation, and that is properly captured by these models. And finally, the last example that I'm going to show regarding this application is the fatigue failure of a Nitinol Biomedical Stent. So we extend the model to incorporate a fatigue degradation function, as shown before, and model this paradigmatic application of shape memory alloys. Stents are small cylindrical tubes that are placed into blood vessels or arteries to hold the structure open. The goal is to counteract the effects of vascular diseases that are associated with plaque blockages that hinder fluid flow. So to deploy the stent, it is usually crimped, placed in a delivery system, and finally expanded in vivo to within the duct. And then it will undergo a number of systolic and diastolic compression expansion cycles. So predicting its fatigue behavior is key. And we can do so with a phase field model, as you see in the slide, which will tell us where damage starts to accumulate and how superficial cracks will propagate with increasing the number of cycles. And specifically, we see some cracks nucleating after 29 cycles. And here you should be seeing a small video of the stent behavior over several cycles. And I would just like to say that this is a 3D model that has a slightly more than 7 million degrees of freedom. Let me jump now to the second application, functionally degraded materials. Functionally degraded materials are those whose properties change typically along one spatial direction. So for example, you can have a functionally degraded material that has 100% volume fraction of metal on one side and progressively changes to 0% volume fraction of metal and 100% volume fraction of a ceramic at the other side. They're useful to accommodate non-uniform surface conditions and to eliminate stress discontinuities at interfaces. And the interesting thing from a fracture mechanics perspective is that fracture is usually mixed mode as a consequence of these spatially varying material properties. So simple experiments lead to complicated crack trajectories. And the phase field is ideal for this. You can see in the top a comparison with experimental results, how the crack deflection is sensitive to degradation of the material. And in the bottom, you can see a classic computational benchmark. You can see that the phase field agrees well with the predictions from other methods, because it has the capability to predict crack nucleation from arbitrary locations. The calculation doesn't stop when the crack reaches the hole. You can capture how it will nucleate again and how all the way into the complete failure of the sample, and without no need for remeshing in principle. And it can also deal easily with 3D models. You can see that depending on how the material gradient is defined, the crack can propagate in a stable manner, as you see in the video, because the toughness increases along the crack propagation direction, or in an unstable manner, if the properties vary along the thickness or the vertical directions. You can see that it starts in the corner, in the weakest point where the toughness is smallest, and suddenly it jumps across the thickness. Again, one can capture these sudden failures without any convergence issues. And this insight and numerical framework can be used to design fracture-resistant functional integrated materials. Another recent application is the failure of composites. This is a paper just published with my friend and collaborator Wei Tan, where we aim at gaining microscopic insight into the fracture process of fiber-reinforced composite materials. For this, we use a phase field fracture model to model crack growth in the matrix, and then we use a cohesive sum model to capture fiber matrix debonding. And I will just show a comparison with some experiments that have been conducted at India Materials. You can see that we have a 3-point bending experiment, and we can use an embedded cell approach to explicitly resolve the fibers in the area where the crack will propagate. And as you can see, a very good agreement is achieved with experiments, not only in terms of the force versus displacement response, but also in terms of the crack trajectory and the crack extension at different stages of the applied load, so both macro and micro scales. And once validated, we use our virtual platform to characterize and design other composite microstructures. And last but not least, I just want to show one slide of what we have been doing recently in rock fracture. This is a 3D model of the so-called Brazilian test, which is widely used to measure the strength of rock-like materials. And there's some controversy among the experimentalists on where exactly the crack initiates, and we think that phase field can bring insight into this. Yeah, so this essentially concludes the first part of my talk. Let me now tell you about this exciting challenge that is hydrogen embrittlement. So hydrogen embrittlement or hydrogen-assisted fracture is arguably one of the most elusive problems in mechanics of materials. Metals are very sensitive to hydrogen, and we know this since more than 100 years ago. As you can see in the slide, Johnson wrote in the Proceedings of the Royal Society about an extraordinary and remarkable decrease in fracture toughness and breaking strain in iron and steel in the presence of hydrogen. And in those days, you will very rarely see words such as remarkable or extraordinary in scientific papers. But how hydrogen degrades metals is indeed remarkable and extraordinary. One of these effects of hydrogen in metallic materials is how the ductility reduces significantly with increasing the amount of hydrogen. You can see here uniaxial stress strain curves, and if we introduce hydrogen into our samples, for example, by exposing them to hydrogen gas, then we see a very strong reduction in the failure strain. Another important effect is the drastic reduction in fracture resistance. You can see in the slide that with increasing hydrogen content, we go from a fracture toughness on the order of 150 megapascals a square root meter to a fracture toughness that easily goes below 40 megapascals square root meter. And this is a low strength steel. In high strength steels, the reduction in fracture resistance can be of up to 90%. And this is a very important point to emphasize. The susceptibility to hydrogen damage increases with the strength of the steel. You can see here a plot of fracture toughness versus material strength for a given hydrogen concentration, typical of exposure to seawater. And note that high strength steels yield a fracture toughness that is below 10 megapascals a square root meter. So it's almost like a ceramic. We like metals because they're ductile, but hydrogen makes them very brittle. That's where the term hydrogen embrittlement comes from. And this figure has two important implications. One, hydrogen is effectively compromising decades of metallurgical research. We have developed high-performance materials, but we cannot use them. And second, high-strength steels very significantly widen the range of experiments where hydrogen is problematic. When using high-strength steels, very little hydrogen content is sufficient to trigger failures in many applications and sectors where we never heard about this problem before. But before high-strength steels or high-strength alloys were developed, hydrogen embrittlement was a problem closely related to aggressive environments. For example, those typical of offshore structures in the energy industry. However, high-strength steels are very cost-effective, and we want to use them for our buildings, bridges, railways. And this is triggering numerous hydrogen fracture problems across the defense, transport, and construction sectors. And in very benign environments, you can see in this newspaper article that the hydrogen coming from the humidity is sufficient to bring structural integrity problems to one of the most famous skyscrapers in London. And last but not least, hydrogen could be the solution or one of the solutions to our energy crisis. We already have hydrogen-fueled cars, trains, and buses in the market, and you can imagine how problematic it's going to be to store and transport hydrogen to power all those vehicles. So given the magnitude of the problem, you might wonder, How can it be that almost 150 years after Johnson's paper in the Proceedings of the Royal Society, the problem is not only unsolved, but hydrogen-related accidents are becoming more and more frequent? Well, one of the reasons is because it's a very challenging problem that crosses the disciplines of material science, structural mechanics, and chemistry. In broad terms, what we know is that atoms of hydrogen enter the material, migrate fast through the crystal lattice, and are attracted to areas of high hydrostatic stress or high volumetric strains, where the lattice expands and there's more space for the hydrogen. But then in the fracture process zone, the hydrogen interacts with the material in many different ways and at multiple scales, changing the bonding strength, the dislocation mobility, stabilizing vacancies, and so on. So the physical picture is complicated, and this makes the development of predictive models for hydrogen-assisted fracture a very challenging task. So it's a very beautiful problem because it's scientifically very challenging and very fundamental, but at the same time, it has very strong and direct implications for society and engineering practice. So you can see that here that this lack of scientific understanding comes at a great cost. Two examples are the failure of bolts in the San Francisco Bay Bridge, with a repairing cost of $45 million US, and the cracking of pipelines in the Kashagan oil rig, which had a repairing cost of $3.6 billion. So I guess one could argue that as an engineer and a scientist, it's very rewarding to work on these kind of problems that are at the same time fundamental and applied. So basically, I aim at solving or trying to solve this long-standing challenge of developing a predictive model for hydrogen embrittlement. And to do so, I divided my efforts roughly into 4 research fronts. First, it is important to accurately characterize the stresses ahead of the crack. And this is not only relevant because brittle failure will occur at a critical stress, but because, as I mentioned before, hydrogen accumulates in areas of high hydrostatic stress. So you need to characterize your stresses properly. And the key step here, or in any research problem, is to identify what are the critical variables of your problem, hydrogen concentration and stresses in this case, and what is the critical length scale. There's an obvious trade-off between computational cost and precision. We're still very far away from being able to use discrete dislocations or atomistic approaches to model real components. But if all the interesting things are happening in the first 3 atoms ahead of your crack tip, then you need your efficient continuum material model will not have enough resolution. And the problem with hydrogen embrittlement is that the critical distance is very small, a few microns ahead of the crack. So we're only going to be able to properly capture the physics if we use some sort of discrete dislocation model. But since we want to impact engineering practice, we are constrained to use continuum models. So the alternative that we have explored is to enrich our continuum models with the physical effects that you're missing at the critical distance of your problem. So introduce the physics implicitly by changing your constitutive equations. And at a few microns ahead of the crack tip, the main effect that you're missing is that conventional continuum plasticity models cannot capture the dislocation hardening mechanisms associated with geometrically necessary dislocations, GNDs. So we have developed a new multi-scale plasticity model, so-called strain gradient plasticity models, that can capture those dislocation hardening effects and the stress elevation that is associated with them. You can see here crack tip stresses versus distance ahead of the crack tip, how big the differences are when you go into the micro scale. Most of these models are higher order, implying that you have gradients of plastic strain, and higher order stresses work conjugate to those gradients. So one has to use mixed formulations to implement them numerically. But I won't get into those details today. The key thing is that you need to resolve those dislocation hardening mechanisms if you want to predict precisely what is your stress level and your hydrogen concentration at your critical distance. The second research front involved gaining mechanistic understanding into what is hydrogen doing at the fracture process zone. This is another key step because hydrogen interacts with metals on many different scales and in many different ways. We will never be able to model a wind turbine atom by atom, so the challenge lies in separating first-order effects from second-order effects and incorporating the key ingredients into our model. The key goal is to understand how hydrogen changes the fracture mechanism in metals, why instead of being ductile, they fail in a brittle manner, with often cracks propagating through the grain boundaries. I tried to interrogate the experiments and apply a mechanics rationale to identify what are the first-order effects. And eventually I came to the conclusion that there were 3 pieces of information that were key to understand the physics of this problem. First, we can see that when doing atomistic calculations, the bonding strength between metal atoms is reduced by the presence of hydrogen. So that is the first key ingredient to develop a mechanistic understanding. If we have a lot of hydrogen, then the cleavage strength or the grain boundary strength will be weaker. So then the next question becomes, okay, how much hydrogen do we have? How full of hydrogen are our grain boundaries? And the answer comes from the chemistry. The well-established mass diffusion laws for hydrogen transport tells us that it is actually very energetically favorable for the hydrogen atoms to reside in grain boundaries. And this is actually what they see in the experiments. This red region here is a grain boundary, and you can see that it's completely full of hydrogen. So our grain boundaries must be much weaker. And if we couple these two ingredients with our enriched description of crack tip stresses, then we see quantitatively that the stresses are not high enough to trigger brittle failure in the absence of hydrogen. That is why metals fail in a ductile manner. But when you take the role of hydrogen into account, then you lower the cleavage strength sufficiently such that your dislocation hardening and enhanced stresses are high enough to hit the cleavage or grain boundary strength, and brittle fracture occurs. So we have learned what happens, or so we think, and if we incorporate this physical effect into a model, we can capture this ductile to brittle transition without any arbitrary decisions or fitting parameters. And this takes me to the third step. We not only want to get the physics right, we also want to get the chemistry right. We want to know precisely how much hydrogen we have, where, and when. And to capture how much hydrogen we have in the fracture region, we work on two fronts: developing chemomechanical models of hydrogen diffusion, but also developing multiphysics models that resolve the electrochemistry and the electrochemistry diffusion interface. I want to know if I have a wind turbine in the middle of the sea, how much hydrogen is coming inside of my metal, and where is it going and when. This involves the development of multi-trap models for hydrogen diffusion, but also new no-main type generalized boundary conditions to resolve the electrochemistry diffusion interface. I won't get into technical details, but I will just say that we have seen very significant difference with the prediction from previous, more simplistic approaches based on prescribing a constant hydrogen concentration. And the last step is to couple all of these ingredients into a computationally robust framework that not only has the proper physics and the proper chemistry, but the capability to deliver predictions at scales relevant to an engineering practice. And I feel that this is very important. It is very important to address these challenges on the computational side, because I have the personal ambition of enabling virtual testing in the energy sector and hydrogen-sensitive applications in general. As you know, virtual testing saves a lot of money to the automotive and aerospace industries. They mostly crash cars and computers these days. And extending this vision to more challenging areas where the environment compromises the durability of materials requires not only a deeper material science understanding, but also the development of sophisticated computational schemes. The facial method is a good candidate for this because it can easily be coupled with the modeling of other physical phenomena. Just to provide an example, one effect that you would like to capture when modeling hydrogen diffusion and fracture is how the hydrogen concentration of the environment follows the crack tip as it propagates. So if you have a crack propagating in a wind turbine monopile, you will expect the seawater to immediately occupy the newly created crack surface. This can be achieved very easily using a penalty approach, as you can see in the slide. And the way we bring in the reduction in fracture energy with hydrogen content is by establishing a direct quantitative connection with the atomistic calculations that I've showed you before, which tells us how the surface of fracture energy is reduced with hydrogen content. So we can run atomistic calculations offline and then use them to define a degradation law that has no fitting parameters. And this is inspired on previous work by Michael Ortiz using cohesive elements. So at the end of the day, what you have in the most complete version of the model are the following residuals for each of the primal kinematic variables and the following system. So we couple all of these ingredients into a computational model, and I will just conclude this part by showing some representative results, hoping to convince you that we have a useful tool that not only can anticipate the outcome of laboratory experiments, but can also be used to impact engineering practice. For example, what you see in the slide is a comparison with experiments on pre-charged steel bars, showing a promising agreement. Here you see a set of interesting experiments where different duplex stainless steels were held at a constant load in a seawater bath. Each sample is subjected to a different constant load, hoping that one of them will never fail, but all did, as you can see in the slide, so the symbols are the experiments. What we can do with our model is not only to reproduce the experiments, but also to run simulations over very large timescales to see what is the critical stress below which engineers can load their structure safely. We have also used this virtual tool to gain insight about the suitability of standardized tests, learning, as experimentally suspected, that early cracking occurs in SSRT experiments, compromising the suitability of the most widely used laboratory test for measuring hydrogen susceptibility. We have also conducted virtual fracture experiments, capturing the effects of increasing hydrogen concentration and loading rate on the crack growth resistance of the material, and showing that the model naturally captures a shift between ductile and brittle failure once hydrogen is introduced into the system. I don't have time to get into details, but the key thing is that brittle interface, such as grain boundaries, will only fail if hydrogen, in our model, if our hydrogen has been introduced into the system. And one can also use this virtual tool to simulate any kind of experiment, minimizing expensive experimental campaigns. Here you can see an Astm experiment to measure the strength of a steel screw anchor on a concrete slab, a problem that not only involves two materials, but also contact, and the complete failure of the screw can be captured, as you see in the bottom right. And these agreements with experiments gave us the confidence to go beyond the lab into field applications, aiming at enabling the virtual testing paradigm that I was mentioning before. These are a couple of examples. The first one deals with a crack propagating from existing pits due to corrosion. The second example simulates a crack propagating in lifting equipment made of a high-strength steel. More excitingly, we can model large-scale 3D problems and correlate our models with inspections and inspection data, creating essentially a digital twin of critical infrastructure. Here you can see a pipeline containing multiple defects due to pitting corrosion that has been characterized by La Rosa and coworkers using non-destructive evaluation, ILI rendering. It is a 12-kilometer pipeline, and we model a critical section of 3 meters that contains more than 100 defects. Note that in the phase field models, because one solves for the damage variable, so to say, as a degree of freedom, it is very easy to incorporate those defects. You just need to assign an initial condition to the nodes located in the damage area, and then you can load at the in-service condition to predict when failure will happen. And this is shown here. Hopefully you've seen the video, and you can see how defects start growing on the top of the pipeline. They eventually merge, 2 of those defects eventually merge, and then that leads finally to the complete failure of the structural failure of the pipeline. So this is loaded at conditions mimicking a riser. And this looks a little bit like a video game, but I should emphasize that it's a sophisticated multi-physics model. Everything is computed on the regional finite element mesh in an implicit Bacar-Euler framework without any convergence problems and fully parallelized, such that it can run in a few hours. So we have a tool that allows us to know how the crack will propagate and when it will propagate, such that we can decide when to replace a component or what are the limit service conditions. And I will end this talk by showing very briefly another exciting avenue of research, the use of phase field modeling to capture how the surface of a corroding metal evolves. We all know that corrosion damage is a big problem for society, and its prediction is a massive challenge for scientists and engineers. In fact, the vast majority of the research conducted in this area is experimental. It has been long considered to be a too complex problem to model computationally. One of the biggest challenges from the computational side is to capture how the aqueous electrolyte solid metal interface evolves, as you see in the image. What you're seeing in the video is a synchrotron analysis of corrosion in stainless steel. And what you typically see here in this video and in others is that multiple pits will form, and they will interact, and under certain conditions they will transform into cracks. And this is quite a challenging problem for many reasons. This bottleneck can be tackled if we exploit the phase field concept and implicitly track the evolution of the electrolyte metal interface. The differential equation for the evolution of the phase field is based more on phase field models for solidification rather than the fracture models that we have been discussing so far. But I won't get into the details for the sake of time. You can find them in the paper. I will only say that we have also incorporated into the modeling the influence of mechanics-enhanced corrosion kinetics and the film reposition and rupture process. And these are just a few representative results to show how the model can capture pitting corrosion and the pit to crack transition, both in 2D and 3D. And we have, of course, validated our model predictions with experiments, showing, as you can see in the slide, what I believe is a very good agreement. So, trying to wrap up, I've tried to cover a wide range of areas, so I had to keep it high level, but I'm happy to answer any questions that you may have. And I'll just give 4 high-level concluding remarks. So first, discovering the face field fracture has been fantastic. It's a physically sound and robust method that can capture cracking phenomena of arbitrary complexity in both 2D and 3D, such as coalescence of multiple cracks, crack branching, crack nucleation from arbitrary sites, complex crack trajectories without any ad hoc criteria, and so on. Also, secondly, we have had a lot of fun with this technology, and we have tried our best to contribute to the face field fracture community by developing new face field fracture formulations for shape memory alloys, functionally grade materials, and fiber reinforced composites, among others. We have also exploited this face field paradigm to tackle the long-standing challenge of predicting hydrogen-assisted fracture. The face field method can be easily coupled with other physical phenomena and can accommodate multi-scale material model approaches. So we have built on these possibilities to develop a mechanistic framework that is capable of predicting hydrogen embrittlement in laboratory experiments and also in large-scale engineering applications, bringing to our industrial partners the concepts of virtual testing and digital twins. And finally, we have shown that the face field paradigm can also be exploited to model another long-standing challenge with important technological implications, corrosion damage. And I think that we will see a revolution in this area similar to the one we're seeing nowadays in fracture mechanics. And that's all. Many thanks to my research sponsors, to the industrial partners that have supported us in one way or another, and of course, all of you for your attention and patience. Know that I release all my codes in my website, so please feel free to download them, play with them, and email me if any questions arise. Thank you. Thank you very much.
Thank you so much, Emilio. Really an impressive talk. I think we have time for questions before the Spanish part of the audience, keep gathered together for our annual General Assembly. But we have time for some questions. Yeah, I think Rina has asked for.
Good morning. So my name is Reina from University of Castilla-La Mancha. So first, I would like to say congratulations for the excellent talk to Emilio. I have a couple of questions, and first, I would like to if you can comment a little bit the face field approach for fracture in comparison with, for example, the cohesive fracture, also the damage approach for fracture. This is my first question. My second question is that in the model for the concrete three-point bending test, when you model that part, and how do you deal with the nonlinear part of the fracture?
Yes, let me bring the example. Well, thanks a lot for your kind words and your interesting question. So, in regards to the first question, maybe I can go back a few slides. So, well, it doesn't really matter. We can stay here. In regards to the first question, how does it compare with other methods? I can only tell you about my experience and well, some of the theoretical ideas, of course. I have worked in the area of computational fracture mechanics since I started my PhD. And I've worked with some remeshing algorithms, Quasi-Newton models, XFEM. And while I enjoyed them very much, for me, it was a great pleasure to see the robustness of the face field. I'm used to go to computational mechanics conference, and you will see everyone presenting their methods and presenting outstanding results. And I will naively go back to my desk and try to implement those methods and see if I could get those results. And yeah, sometimes I could get those results, but then I change some aspects of the model, and then nothing will work. So it was a great pleasure for me when I think I attended a talk. I think it was Tom Hughes or Laura De Laurentiis about the face field, and I came back to my desk, I implemented, I saw that I was able to get those fancy videos that they presented in the conference, but also I could change the conditions and the steel was very robust and it was dealing to very nice calculations. So it has been a nice discovery, and from my personal experience, it works much better. So the ideas are similar to cohesive zone models in the sense of a fracture or having a fracture energy. On the other hand, the cohesive zone models do require that you know exactly where your crack is going to propagate. So the phase field gives you a bit more freedom in that sense. And it also seems to be more computationally robust. At least I haven't encountered so many convergence problems. In regards to XFEM, I think the key thing for me is that, while I very much enjoy working with XFEM, it was a bit of a challenge to take XFEM to 3D. Well, with phase field, you can use the same code for 2D and 3D, so it's completely straightforward. And in regards to damage mechanics, well, I think one could argue that phase field and damage mechanics have many similarities. So I guess one idea or one advantage of phase field is that somehow provides a link between discrete fracture mechanics and damage mechanics. The other advantage is that it's non-local, but then of course you could think of, so it has some advantages relative to local damage mechanics models where there's a loss of elasticity and therefore your results become mesh dependent. But you could think of a similar model to those non-local continuum damage models in that sense. It's not that different from a non-local continuum damage model. And your second question was in relation to I hope that answered the first question. And your second question was in relation to the 3-point bending example. So in this case, everything is all the fibers and the matrix are linear elastic. I mean, the problem is non-linear due to the fracture. Yeah, as I said, we haven't seen any convergence problems. This method is quite robust. But we are also running simulations with an elastic plastic matrix, for example, and they seem to be working well so far.
So the fracture part is basically linear elastic. Is that true?
So the material is linear elastic, and then of course the fracture in the bulk is dominated by the fracture energy of the material, so by the Griffith or the phase field balance equation, and then you have a cohesive zone model between the fibers and the matrix to model the debonding process. Yeah.
Okay, thank you.
Thank you.
Hi, I would like to ask something.
Yes, Xavi Oliver.
Yes. Thanks, Emilio, for this very nice talk. I'm really proud of having people like you in SEMNI, and the new generations are just going so far. And I would like to ask you a question about applications of phase field models. So phase field models that were explosive in the last have been explosively increasing and performing in the last years, especially when the problems of computational cost has by remesh have been overcome by remeshing of everything. That was the main criticism that was allocated to this kind of methods. But now I wonder, since they are really efficient and well suited for a large number of problems, but in principle, they are problems which try to capture a discontinuity. So jam in the displacement field, what we call the strong discontinuity, okay? But there are other problems also interesting in computational mechanics, in engineering, where the relevant is not the discontinuity in displacements and velocities and whatever, but the discontinuity in gradients of displacement velocity. That is what is called, as you know, weak discontinuities, shear banding, and also other problems in which the discontinuity is not propagating in the sense that, so axially, in the sense that they just extend the line of the discontinuity, but keeping the path before in previous stages. But like the problems like, for instance, shock propagation, shocks discontinuity. So do you think that there is some room for this kind of phase field models to work on this kind of problems?
Yeah, thanks a lot, Xavier Oliver, for your nice words. And I should apologize because I have only my experience in fracture mechanics is limited to X-ray cohesive models and the like, but I have heard very high praise of strong discontinuity methods that Xavier Oliver and others have pioneered, and they seem to work very well. And they have many, and to the best of my understanding, they have some similarities as well with these methods and are also very powerful. So yeah, in regards to your question, I agree that one maybe criticism that one could argue is that you need to resolve this fracture length scale. In the same way, I guess, that in other methods like cohesive models, you have a fracture energy and that automatically triggers a length scale. So you have always a fracture length scale that you need to resolve, and that comes at a certain computational cost. So maybe it was not possible 20 years ago or 10 years ago to really see the explosion in phase field applications that we're seeing these days, because now finally those computational scales are coming into our grasp, and finally we can deal with these very large problems, while at the same time having a refined mesh. So I completely agree on that, and I reiterate my apologies for not emphasizing that there were other alternatives that have been working very well through the years, these strong discontinuity approaches. In regards to the last part of the question, my experience is limited to computational fracture mechanics, recently to corrosion, and I'm aware of the microstructural evolution models. But there have been some papers in dealing with shear banding as well, and also explicit dynamic calculation. So the group of Tom Hughes has been doing quite a lot of dynamic explicit, and also Hein Weissman at the University of Columbia have been doing it. I don't want to get too much into the details because I'm not very familiar with them, but my impression from listening to them and from getting a quick overview of their papers is that it's working well in those areas as well. So hopefully the method can be useful there as well.
Okay, thank you.
Thank you.
Well, I think there is no other question, but I would like to end by asking you one question, which is purely motivated by a practical interest. What is the solution, the practical solution to hydrogen embrittlement? Because from your talk, it seems that the only solution is to be sure that your stress threshold is well above the level of stress during the service in your part. So it seems that the solution is to live with it. Is there no other solution to the practical?
That's a good question. Yeah. So I guess what we're doing at the moment is, or what we ambition. Thanks for the question, Elias. So what we ambition is to develop some sort of a magic sphere that will tell us what's going to happen in the future. So if you pick this material and you are in this particular application, are we going to see a hydrogen-related failure or not? And we know that some materials are more susceptible than others. So we should be able, but your point is a very good one, because you could argue, for example, we know high-strength steels, modern steels, are very sensitive to, very susceptible to hydrogen embrittlement. So you could argue, okay, so you're only bringing us bad news. That means that there's no way that we can get around it. We will just need to give up on using these modern materials that have many other advantages. And I guess for the moment that is the case. There have been attempts, and we have been involved in some of them, in trying to go from analysis to the design of hydrogen-resistant materials. It is not an easy task. There are some cases where you can design some hydrogen-resistant materials. So we know, for example, that there are some microstructural traps that will basically retain the hydrogen and will not allow the hydrogen to diffuse to the fractured region. So in some applications where you have a limited amount of hydrogen, it is possible to develop this sort of materials that will be able to take in more hydrogen without releasing it to the fractured region. However, as you can imagine, if you have a pipeline in the middle of the sea, then the source of hydrogen is going to continuously be there. So you're going to have a permanent source of hydrogen. So those traps eventually will saturate, and hydrogen will still be available to damage your material. So it's not an easy solution, and I hope that we can find a solution, because, as I said, it could be a big bottleneck to the development of one of the most promising solutions to our energy crisis. So we're working on it. We're working on it. Maybe for the next SEMNI conference, I have something to present.
Sure. Well, Irene had some questions. I saw you had the hand up.
Yeah. I had a question, but I think in the interest of time, maybe. But yeah, I'd like to congratulate, of course, Emilio on the prize and on the excellent talk, and thank you for it. It was really interesting and comprehensive of the different applications that you have worked on from the perspective of phase field. My question was, you can answer it shortly if you can. It was related to your experience with dynamics phase field models for fracture, if you have any, especially for the applications regarding domain evolution in various materials that you've showed, and if you had any with experience with dynamic fracture, and what is it?
Yeah, I'll try to answer briefly. So my experience in dynamic fracture modeling with phase field is limited, although I can see the potential because you can have all these effects that are triggered by the waves, and you can capture those. This is an example of a dynamic fracture calculation, which we have used an implicit method as well. So there are some challenges related to the implementation in explicit approaches, and there has been Yuri Vasilevs in Brown has proposed a few alternatives to the methods, and Tom Hughes has done quite a lot of dynamic fracture. So my experience is limited. It has worked well so far, and I can see that it captures the effects of these waves. But of course, this also comes at a computational cost. You need to resolve the phase field length scale, and you need to resolve this stability time, so to say. Yeah.
Okay, Emilio.
Yeah. Thank you very much.
If there is no other question, I think it's time to thank you again for this wonderful lecture. Again, to congratulate you for the prize, and I hope to see you soon, both in the Spanish community and in our conference, and hopefully elsewhere. Let's see if 2021 gives us the opportunity to meet somewhere in the world. So again, thank you, and
thanks a lot, Elias. For sure, you'll see me. Yeah, and I think I have to disconnect because I need to use my other email account to connect to the assembly. So I'll stop sharing
to the General Assembly. Of course.
And I like, if you allow me, I like to thank everyone who joined for making jointly with Emilio this seminar a success. This is our first experience organizing a SEMNI seminar, and we're really thankful to Emilio and to everyone who participated. Thank you.
Thank you all. Thank you.
Thank you.